In this segment, we'll be solving linear inequalities, and the solutions to linear inequalities are inequalities, and that implies that our solutions will be infinite in nature. So to show them, to illustrate our solutions, or I should say our solution sets, we are going to use intervals along the number line. And there are a lot of ways to show those intervals along the number line. Let me show you a couple of ways. Suppose we are trying to illustrate or show that 2 is less than or equal to x and x is less than or equal to 5. Now that's the interval between 2 and 5, but including the 2 and the 5. Now graphically, it's just that we identify a 2 and a 5 along the real number line, and we say, gee, we want to include the 2, so we put a bracket notation at 2, and we want to include the 5, so we put a bracket notation there, and we shade between the two numbers. Now, this interval is said to be bounded because we have a bound on the top side and a bound on the bottom side. We have boundaries on both sides. This is also called a closed interval because the endpoints of the interval are included in this group of numbers that we are describing here. There's another notation called interval notation, and it works like this. We want the interval from 2 to 5 and including the 2 and the 5, so we would use interval notation like this. The interval from 2 to 5 including the 2 and including the 5. Now, here's another inequality, very similar, but 2 is strictly less than x and x is strictly less than 5. So although we want the values between 2 and 5, we don't want to include the 2 and the 5 because of these strict inequalities. So we use a parenthesis notation on either end of our interval. Now again, this is a bounded interval. We have bounds here. The situation is unbounded when we're talking about infinity in either direction. Now, this is called an open interval because the endpoints are not included. And the interval notation works like this. We're talking about the interval from 2 to 5, but we're not including those endpoints, so we just use parentheses. Now, this one is very predictable. We have a situation where we have 2 is strictly less than x, so 2 is not included in the interval, but x is less than or equal to 5, meaning that 5 is included. So for 2 not to be included, we use parentheses, and for 5 to be included, we use brackets on that end, and we shade between the two numbers. Now this again is a bounded interval, and the interval notation is that we go 2, 5. Now look back over here. We don't include the 2, but we do include the 5. So we have a parenthesis on one side and brackets on the other. Here's another situation. We have x is greater than or equal to 5. In situations like this, a lot of times it's valuable to put some other numbers on the number line other than the one that you see here. Even though we kind of agree that the positive numbers lie to the right and negative numbers to the left, it's kind of a little bit of redundant accuracy here to put a 4 and a 6 on either side of the 5 to give that kind of reference. At any rate, if we want to illustrate x is greater than or equal to 5, then we would do this, greater than or equal to. So we're going out to the right like this, and we're talking about including the 5 like that. So there's our graph. Now this interval is unbounded because there is no boundary out to the right. So an unbounded interval. And the interval notation here is from 5 to infinity, and the 5 is included, but infinity has no last value, and therefore it is open on that end. Now, if x is strictly greater than 5, very similar idea. We're talking about shading to the right of 5 like this, shade the arrow as well. We don't want to include the 5, so we use a parenthesis notation here. Again, an unbounded interval, and the interval notation is 5 to infinity, but not including the 5 and never including the infinity. For this one, x is less than 5. We're just going in the other direction. Very similar idea then. We shade to the left of 5. We don't include 5 by indicating parenthesis here. Shade an arrow on this side as well. The interval notation is from negative infinity to 5, never closing on the infinity side, you see. And we don't we don't close the interval on the other side as well because we have a strict inequality. Well, let's talk about solving inequalities. We're going to find out that solving linear inequalities is very similar to solving linear equations. That is, we can add on both sides, subtract on both sides, multiply and divide on both sides of the inequality. There's just one little nuance that's very different from solving equations, and I'll mention it when we get to it. Here, we would, if we're solving in the same way that we do linear equations, then we would look at the expression on both sides and simplify the two expressions. Now here I'll perform the indicated operation giving 4x plus 4, and on the right I'll just bring down. Now I'd like to isolate the x by putting all the terms involving x on one side of the equation and the constants on the other side as kind of a first order of business from this point. If I subtract 2x on both sides, I'm going to leave 4x here. I'm going to subtract 2x over here and subtract 2x over here. And I'm also going to subtract 4 on both sides, so I'll have 3 minus 4 on the right. Collecting over here, I get 2x, and on the right I get 3 minus 4, negative 1. Then I divide on both sides by 2 to find x to be less than negative 1/2. Now, that means that for all values of x that are less than negative 1/2, we have truth in our original inequality. We can actually check a few of those values. It's not possible to check all of the values because we're talking about an infinite set of numbers here. And we could illustrate our solution here by using interval notation or a graph and that kind of thing. We already know how to do that. Here's another one. This one involves a fraction. Recall that when dealing with fractions in linear equations, we treat as a first order of business the removal of those fractions. And we accomplish that by identifying a common denominator and multiplying through by the common denominator. Here the denominator, the only denominator is 2, so it's the common denominator. So we're going to march through and multiply every term by 2. So we're doing this. Now I know it's real easy to do this in your head for this particular problem, but we want to establish the habit of showing that common denominator times each term so we won't forget to do it in the more difficult problems. 2 times 1, 2 here. The 2's go out, minus 3x. And then on the right we have 2x minus 8. I'd like all of my terms involving x on one side. Once again, I'll elect to put the terms involving x on the left and the constant terms on the right. I have minus 3x already over here on the left. I'll subtract 2x on both sides, giving me minus 2x on the left. On the right I have the minus 8, and I'm subtracting 2 on both sides to remove this 2. So I have minus 2 over here. Collecting here I get negative 5x. Collecting on the right I get negative 10. Now here's where the little nuance I was talking about comes into play. It turns out that whenever you have occasion to either multiply or divide by a negative amount, you have to change the sense of the inequality. Now, changing the sense of the inequality means just changing the direction of the little inequality arrow. So here, when we go through the step of showing that we divide by negative 5, we change the sense of the inequality like that, and then go about our business as we normally would. Here the negative 5's go out. We have x is less than or equal to 2. Now, let's talk a little bit about this. This is a great opportunity to make a mistake. And often mistakes are made here because students have the tendency of looking at this step and saying, okay, all I need to do is divide by negative 5. So the tendency is to just draw the line and put negative 5 here, draw the line and put negative 5 here. And if you have that habit, you're going to probably forget occasionally to change the sense of the inequality. So that's why I've encouraged the idea of writing this step in other kinds of problems. All right, let's talk about why the sense of the inequality needs to change in this circumstance. Also, I want to tell you, while I'm erasing here, I'll tell you that it's much, much more often the case that we're dividing by a negative than multiplying by a negative. You see, we often come upon a situation where we have a negative coefficient that we need to divide by on both sides of equations and now inequalities. But it's not very often that we would be multiplying by a negative amount. You know, when we multiply through equations and inequalities, just conceptually here, that usually that happens when we are clearing fractions. We do that as a technique to clear fractions. Well, denominators of fractions are not usually negative amounts. So we don't have occasion to multiply by negatives very much, but we do have a lot of occasion to divide by them. Well, I'm going to use, to illustrate the situation, I'm going to use that unusual case of multiplying by a negative just because it's easy. Consider a number line and consider that, we know that, let me put a 4 in here. We know that 2 is less than 4. Now look at what happens when we multiply by, let's say, something as simple as -1. So we multiply by the same amount on both sides. Here we get -2, and here we get -4. Now look at what's happening on the number line. When I multiply this by -1, the value becomes -2. When I multiply -1 times 4, I get a kick over to this side. I need a -4 over here to kick it over to. So we get a kick over to the other side like this. Now, inequalities are all about order relationships. 2 is less than 4 because 2 lies to the left of 4 in the number line. But when we multiply by -1, look at what happens. Boom, they're in a different order. So it changes the order of things. That's what the multiplication by negatives is all about. So that's why the sense then needs to change. Now you can see it's even clearer when we have something like, let's say -2 is less than, let's say, 3. You see, and in that circumstance, we start out with this number and that number. -2 is to the left of 3. And when we multiply by -1, boom, they go to the other side of the number line. You see, they go to the other side of 0 on the number line is what I'm talking about. So when you multiply by -1, we get 2 over here and we get -3 over here. So the -2 has gone over to the 2, and the 3 has gone back to the -3. So that's what's happened. They just they did this, you see, changing the order once again. So that's why all of this works out. Here's another one now. This one is called a double inequality because really it's 2 inequalities in one statement. We've seen it many times in the past, I'm sure. This inequality and then this inequality is the way we read it. We say 1 is less than 2x plus 3 and 2x plus 3 is less than 9. To solve this inequality, which means to find the value or values of x that will cause the inequality statement to be true, we simply isolate x in the middle part. Now to do that, we use all the techniques that we have used in the past. We can add, subtract, multiply, and divide. And we have to bear a couple of things in mind. We have 3 parts here, for one thing. We have a part here, a part here, and a part here. So whatever we do in one part, we have to do in all 3 parts. That's one thing. The other thing is that if we have occasion to multiply or divide by negative values, we have to change the sense of the inequality. And that means changing the sense in both places. All right, let's go about the business of isolation here. We want to isolate first the term involving 2x, and to do that, we'll clear the 3. Now to clear the 3, we subtract 3 in all parts. We could write 1 minus 3 here. We could write this expression minus 3. We could write 9 minus 3. That's a safe thing to do. Another technique is to just put minus 3 underneath like this. It's kind of an elementary way of looking at it, and I've even seen students do that just for emphasis. But 1 minus 3 would be -2, and then the 3's go out here, leaving 2x. And then 9 minus 3, 6. Now, to clear the 2 coefficient, we divide by 2, but if we divide by 2 here, we have to divide by 2 in the other places as well. So here's what we're doing, and I want to show this step just in case I have a situation later where I'm dividing by a negative. I want to make sure I get that the sense of the inequality is changed. Okay, we're not dividing by a negative here, no sense change, so -2 divided by 2 is -1, and the 2's go out here, isolating the x as expected, and on the right, 6 divided by 2 is 3. So x then is between -1 and 3, not including either of those endpoints. And once again, we could construct a graph here, or we could use interval notation to illustrate this solution set. When absolute value appears in inequalities, it's important to think about the fundamental idea of absolute value. And our original definition had to do with distance from 0 on the number line. So if we see the absolute value of some x being less than 3, it means that we're trying to identify those numbers whose distance from 0 on the number line is less than 3. And on the number line, let's see, distance from 0 is less than 3. That means all of these values and also all of these values, you see. So we're talking about an interval from -3 to 3 to make that statement of inequality true. And as a double inequality, we could describe the situation as this, that -3 is less than x and x is less than 3. So it's the x values between -3 and 3, not including those endpoints. Now we could separate this double inequality into two separate inequalities. If -3 is less than x, it means that x is greater than -3. And here, if x is less than 3, x is less than 3. Okay. So, and we want, if we're thinking about this as a set of values, and this is a set of values, then we want the values that are in this set and in that set at the same time. That is, we want the overlap of these two. Let me show you what I'm talking about here. It's important whether we put the word and the word or in these problems. So we want values that are in this set and in that set at the same time. Now, that's the notion of intersection when we talk about it's kind of a geometric thought process in this. But if we're talking about, here's -3, here's 3. If we're talking about x being greater than -3, we're talking about values that start here at -3 and go out this way infinitely far. And if we're talking about x being less than 3, we're talking about values that start here and go back this way infinitely far. So we're not talking about all these values that make that true and all values out here. It's only the place where these two sets overlap. It's the intersection of those two sets, you see, that we're talking about. So that's why the word and is so important here. We want values that are in this set and in that set at the same time, intersection notion. Now when the absolute value statement, the inequality statement with absolute value in it, is greater than or equal to, same idea, we think about distance here, the distance is greater than, in this case, or equal to 3. Okay, that means beyond 3 in both directions. So we're talking about values that lie out here that make that true, you see, and values out here that make that true. Now since we have a non-strict inequality, we're going to include the -3 in this, so we are talking about a bracket in these positions. So we're kind of outside of an area. And now, for what values is this true? Well, it's true for all the numbers out here as well as all the numbers out here. So rather than the intersection of two sets, it's the union of those two sets of points, you see. Now, as separate inequalities, and by the way, the double inequality idea kind of doesn't apply here. The double inequality occurs when we can kind of nest the values between two bounds, you see. And here we have an unbounded situation on both sides. But we can describe these with separate inequalities. This set is described as x values less than or equal to -3. And this is x values greater than 3, greater than or equal to 3. Now, the word or is used here to indicate that we're talking about the union of the two sets. We're talking about all the numbers that are in this set as well as all the numbers that are in this set that make that statement of inequality true. All right, let's look at some more complicated absolute value inequalities. Before we even start, though, I want to tell you that there are actually two ways to get ourselves into a logic pattern for successfully solving the absolute value inequality, all of them. And one way is a little more mathematically sound than the other. My suggestion is this way, and this is the one that's mathematically sound. You think about the situation in terms of distance from 0 on the number line. The distance from 0 on the number line, you see absolute value here, is less than 6. So just imagine a number line and that you want numbers represented by this expression that are less than 6 and greater than -6. And then set up your two inequalities according to that idea. You want numbers represented by this expression that are less than 6 but greater than -6. You see, so the x minus 7 then is greater than -6. All right, that's the idea. Now, since we are talking about that little confined area that we were discussing earlier, we're talking about the word and here. And we're talking about the notion of the intersection of the two sets of numbers that we have represented here by the two inequalities. All right, let's solve each one of them. We're adding 7 on both sides here to find x to be less than 13. And over here, we're adding 7 on both sides to find x to be greater than 1. All right, so we want x to be less than 13, and at the same time, x is greater than 1. So we want the values of x that are between 1 and 13, and not including those endpoints. Now, I said that there were 2 ways to get yourself into a problem like this. There are 2 ways to set up the inequalities for solution. Now, one way is that distance notion, which is highly mathematically sound and the one that I suggest. Another way was pointed out to me by my students. And they're telling me that, well, gee, if we take kind of a mechanical approach to this, we can correlate this well with the experience of having absolute value in equations. And with equations and absolute value, we just separate into 2 cases. And remember, one case was to write the expression in the absolute value symbols equal to the other number. And the other case was the expression equal to the negative of that number. All right, let's use that idea. There's just one little change in that notion. If we drop the absolute value symbol, you see, symbols, and then write the inequality as we see it, we have one of them. And if we drop the absolute value symbols and tack on a minus sign over here and change the sense of the inequality, we have the other one. You see, so that's our 2 cases. And then I said, yeah, but what about the notion of and or? And they tell me, they say things like, well, we have less than and when it's greater, it's or. You know, it's not very mathematically sound, but it works incredibly well. All right, let's consider another one, and we'll look at it again both ways. Looking at this problem in terms of distance, we want the distance from 0 on the number line represented by this expression to be greater than or equal to 5. And that means that we want the numbers represented by this expression to be greater than or equal to 5 or less than or equal to negative 5. So those then are our 2 expressions, our 2 inequalities. We want that to set that expression to be greater than or equal to 5, and then we want that expression, the numbers represented by the expression, to be less than or equal to negative 5. The idea of distances along the number line to be beyond 5, you see, in either direction. So that these numbers have to be greater than or equal to 5 or less than or equal to negative 5 for that to be true. Now, the notion of distance having a portion of the number line over in this direction and a portion of the number line over in this direction represent our solution set means that we want the union of those 2 sets. So it's the idea of or here. The word or belongs in here. Now, the mechanical way of dealing with it is like this, that one equation emerges by taking off the absolute value symbols and writing down the inequality. The other emerges by taking off the absolute value symbols, tacking on a minus sign, and changing the sense of the inequality. That's what we have here. Okay, so our 2 inequalities. Let's solve them. Multiplying by 2 on both sides here, we get x minus 3 is greater than or equal to 10. And then adding 3 on both sides, we find x to be greater than or equal to 13. Over here, multiplying on both sides by 2, we find x minus 3 to be less than or equal to negative 10. And adding 3 on both sides, we find x to be less than or equal to negative 7. So now the word or is in here, remember. So we want x is greater than or equal to 13, or x is less than or equal to negative 7. Graphically, I think is a very good way to kind of show this, this situation, to illustrate it. X is greater than or equal to 13. Let's put 13 out here and negative 7 over here. And we want x values greater than or equal to 13. That's x values that are in this interval. So those are all solutions. And the other solutions are to the south side of negative 7. So x is less than or equal to negative 7. That's these guys with a bracket notation right here.